In today's world of portable electronics, ranging from our smartphones to our laptop computers, as well as electric vehicles and grid storage systems, batteries play a significant role in providing the energy we need to make these products work. One of the most common batteries is lithium-ion based, which is popular because it is rechargeable and can provide a lot of energy in a small volume. One use of lithium-ion batteries is in electronic cigarettes, often called e-cigarettes. An e-cigarette is an electronic nicotine delivery system. It generally consists of a cartridge containing a nicotine-based liquid and an atomizer, which is heated from electrical circuit generated from a battery. When the user inhales, the airflow activates a flow trigger, and the battery heating vaporizes the liquid into a smoke. As is the case with all cigarettes, e-cigarettes are not healthy. However, lithium-ion batteries pose an additional safety risk due to the presence of the battery itself, which consists of flammable electrolyte and oxidizing agent, which can ignite and cause fires and explosions. In fact, there have been numerous e-cigarette battery explosion incidents. These have resulted in bodily injury, including severe burns to the user's face, chest, hands, and legs. For example, on November 23, 2016, an e-cigarette exploded in the pocket of a 31-year-old employee of a wine store. The explosion and fire caused the employee to undergo major skin grafting surgeries. Lithium-ion batteries used in e-cigarettes typically consist of sheets of positive and negative electrodes, which are spaced apart by a separator, filled with a liquid electrolyte, wrapped into a cylindrical shape, and placed into a metal case. Due to the inherent safety risks associated with these batteries, a battery management system should be used to control voltage, current, and charging levels, and keep them within safety limits. However, a battery management system may not be able to prevent catastrophic failure if there are defects present in the battery. Defects can get introduced into a battery during any stage in the manufacturing process. Some examples include non-uniform coating of the electrode on current collector, pinholes or absence of coating, blisters or agglomerates in the electrodes, holes or weakness in the separator, and clogged separator pores. Other assembly-related defects in lithium-ion batteries include the presence of metallic contaminants, non-uniform positioning of electrode layers, stacking of positive and negative tabs adjacent to each other, metal protrusions on the tabs and current collectors, and improper tab welding resulting in burns that can tear the films. This CT scan image of an e-cigarette battery shows that the deflected anode overhangs near the positive terminal of the battery, which may cause a short circuit between either anode layers or with the nearby cathode layers. This was one of the problems identified by Samsung in its recall of the Samsung Note 7. All these defects can cause internal short circuits and localized heating, which can lead to thermal runaway. Thermal runaway is a process which occurs when the temperature of the battery increases uncontrollably and rapidly due to the self-heating, exothermic reactions, and thermal decomposition of battery components. During thermal runaway, battery temperatures can reach as high as 900 degrees Celsius and can generate flammable and toxic gases. Because the case of the battery is metal, this cell is like a pressure bomb when thermal runaway occurs, releasing toxic gases including hydrogen fluoride and carbon monoxide. So how do defective and substandard batteries enter the e-cigarette market? Unfortunately, some manufacturers do not employ sufficient quality checks, or unauthorized retailers and suppliers may be deliberately selling mislabeled or poor quality batteries, including defective, substandard, degraded, and damaged batteries, which they purchased and rewrapped under their own brand name. Counterfeit batteries are also a problem. These batteries visibly appear to be made by the original manufacturer, but are actually replicas that may differ in design, materials, and ratings, and have poor quality and reliability. To pave the way for better performing, more reliable, and safe lithium-ion batteries, the battery team at the Center for Advanced Life Cycle Engineering, CALS, at the University of Maryland, have been conducting both theoretical and experimental research. One effort pertains to the study of dendrites that can short-circuit the positive and negative electrodes in a battery. CALS has implemented a unique approach to provide a window to look inside the battery while the battery is operating. We assemble the sample in a glove box in an ultra-high purity argon atmosphere. During the dendrite growth process, both the real-time voltage data and the real-time dendrite images are collected. Our test results illustrate both the dendrite growth process and the corresponding voltage change. We also conducting testing into battery explosions, the gases generated during thermal runaway, and the safety issues with the storage and transportation of batteries. While there have been many reported incidents of e-cigarette battery fires or explosion, including 17 cases of e-cigarettes exploding or catching fire in airplanes in 2017 alone. Unfortunately, at this time, there are no standards or regulations for e-cigarettes or the batteries that are used in e-cigarettes. At the University of Maryland, we are trying to provide guidance for companies, regulatory bodies, and consumers. With the growing popularity of e-cigarettes, it is paramount that both manufacturers and consumers understand the dangers of these devices and the batteries that they purchase. Some e-cigarette manufacturers are not testing properly, and in some cases, rewrapped and counterfeit batteries are entering the marketplace. Customers must be extremely cautious, not only of the health issues with smoking e-cigarette, but also the risk of explosion in these products.